So I was trying to convince you that these considerations of Einstein with the Einstein elevator and stuff like that, they led him to considering that basically the gravitational field is described by the metric, and so if you just have flat space but written in curved coordinates, in general coordinates, you can obtain this metric as a coordinate transformation from the flat metric to some general metric, general curved metric. However, a real gravitational field will not necessarily be described by that. And so real gravitational field is still described by the metric, but you cannot find a coordinate transformation which will transform this to the flat metric. We will learn soon what is the criterion, how to actually get to know, given the metric, is it just a flat space written in some strange coordinates, or is it actually a real curved manifold where I cannot do the transformation? And so we will learn that once we discuss the geometry a little bit. So anyway, so now we have this general metric, and it in general has 10 components. It's this symmetric 4x4 matrix. But we know a lot about this metric, because if actually the general relativity is to reduce to Newtonian physics, in particular if the geodesic equation which we derived should reduce to the Newton's law, we know that there exist such coordinates where the GTT part of the metric simply writes as minus 1 minus 2 phi, where phi is the Newtonian potential over c square, and then you treat this as a small perturbation with respect to this one here. So now what really doesn't follow from the geodesic equation is this part of the metric. However, I'm telling you this term is there, and this is the right approximation to Newtonian physics. So from this approximation, if you write this metric down, you not only recover the Newton's law from the geodesic equation, but you also recover the Poisson equation from the Einstein equations. Okay, so that's where this other term comes from. Okay, so we know that this must be the Newtonian limit of the metric. We also discussed this gravitational redshift, and we use this Einstein elevator to actually tell us what this gravitational redshift has to be if you have uniform gravitational field G. In other words, if I have gravitational field and I have some tower of height delta H, then the frequency up here is different to the frequency down there, and then you can calculate the corresponding redshift, and it's simply given by minus G delta H over c squared. So now let us return to this gravitational redshift one more time, but now knowing that actually we have to use the metric to describe our gravitational field. Okay, so gravitational redshift now again. And so we know that in strong gravitational fields, our clock, our proper time, which is proportional to 1 over omega, goes more slowly. Okay, so gravitational field in strong gravitational field time ticks more slowly. So now how you calculate how slow this is you just calculate what is the corresponding proper time of measured in your clock. And so corresponding proper time is just t tau. It used to be, well, d tau square is minus ds square. But now I write it in terms of the curve metric. So it's minus g mu nu dx mu dx nu. And I can use any parameter I want. So I choose to use the time coordinate to be my parameter in this case. So dt and then dt. So I'm choosing one of the coordinates, the time coordinate, to be my parameter here. Okay. So now this is how, what my clock shows if I'm at a given position x. So now you may be considering an observer 1 here and an observer 2 here. And, each of them has their own proper time, d tau, and this guy has d tau prime. And So basically, whatever this observer measures may be different from whatever that observer measures. But if I send a signal from one to another, they should agree on, how that this is changing continuously or whatever. So if I want to know what is the change of frequencies going from one point to another, in other words, what is the ratio of the frequencies one observer measures in one point and another observer measures in another point. So then you have, and now to confuse you, I should be using omega. Well, to confuse you, let's use nu for the frequency now. So nu prime over nu. So the frequency is 1 over time. So that's why this must be the same thing as d tau over d tau prime. I'm just using that the frequency is 1 over time. All right. So now I just express these things here. Okay. So I may be using different coordinates for this observer here and for that observer here. In which case I would have, an observer which doesn't have primes, which is this thing, and an observer with primes. So that would have g prime and dx prime, dx nu prime, dt prime. Okay. So now if you are in stationary spacetimes, so you can show that you can extend your time coordinate everywhere. Okay, so in stationary spacetimes, you will see why later on, but what I mean by stationary spacetimes is that the spacetime, the metric, doesn't depend on time coordinate, and then you can choose the time coordinate t prime to be, we can set t equal to t prime. Okay. Moreover, so what this thing here is telling me is the trajectory this observer 1 or observer 2 is actually sweeping in the space-time. Now, if you have static observers, they are not moving. Okay, so static observers, static observer, the corresponding x mu will be something. Well, x mu is still. What I'm trying to say is that the x mu has only non-trivial component in the time direction, right? So I'm not moving. That's why dxi over dt will be 0. So the only non-trivial thing is dxt over dt. Okay, so static observer only moves in time, but the spatial coordinates remain the same. Okay, so then I can just simplify whatever this relation is. So what d tau is just minus gtt, and then this is dt over dt, dt over dt. So that's it. And then dt. And then the other one is minus gtt. I'm using, well, there's a prime here, there's another prime here, meaning that I'm evaluating it either at that point or at that point here. So let's call this point x, and call that point x prime. So this is at x, and this is at x prime. Okay, so now I said we are in stationary space-time, so dt is the same as dt prime. And then I'm using the same coordinate, so I don't need a prime here. So then you have a very, very beautiful formula. That's just minus gtt at x, and then divided by minus gtt at x prime. Okay, and that's how your gravitational redshift looks like. So this is nu prime over nu. So how your frequency looks like really depends only on the time component of the metric at that point or that point. Yes?
How do you define stationary spacetime?
Our stationary spacetime is, well, for this purpose, it's something where your metric components do not depend on time coordinates. More generally, you say that there's a time-like killing vector which exists in your spacetime, and that means that I can choose basically the time coordinate everywhere the same. So that's why I am saying, the coordinate time here will be the same as the coordinate time there, because throughout the whole space-time, I just simply have one time. Yep.
How do you know you can find frames where t equals t prime and they're both static?
That's my assumption again. So it's hidden in this assumption of stationary space-time. So now I'm really studying the situation where I have an observer at rest here, I have an observer at rest here, and then nothing depends on time in the whole space-time. Yeah, so that's hiding there. You will actually, in your tutorial tomorrow, you will study the situation when one of the observers actually is moving. And then, this becomes more complicated. Other questions? So this is the general formula for the redshift once, the observers are static. So now let's have a look what this gives us in the Newtonian limit. Newtonian limit. And we already know from our calculation in the morning that GTT is just 1 is minus 1 minus 2 phi over c squared. Is there supposed to be a plus? It's supposed to be a plus here, and it's supposed to be a minus here. Sorry for that. All right, so this is the right thing. So then we have that for in the Newtonian limit, nu prime over nu is simply 1 plus 2 phi evaluated at the point x, and then 1 plus 2 phi evaluated at point x prime. Okay, so now my Newtonian limit is valid as long as the gravitational potential is V. Okay, so as long as this thing is much smaller than 1, in which case I can Taylor expand. And so then this thing here will be equal to 1 plus phi evaluated at x times 1 minus phi prime, meaning evaluated at x prime. Okay, and so this is simply 1 plus phi minus phi prime plus higher order terms. Okay, so this is the general formula for how the ratio of nu prime minus nu is. And so then if you have the redshift, which is nu prime minus nu over nu, it's simply, so you have to subtract 1, it's phi minus phi prime. So in the Newtonian limit, you have this thing here. So now you can plug any Newtonian potential you like. So for example, you can consider that Earth is spherical, and you can just use for the potential Gm over R with a minus sign. Or we can just go back and consider our field homogeneous. So if you consider our field homogeneous, and the potential is simply just G times H. And so this thing here will become, of course, minus G delta H. And then, if I recover C squared, this for the homogeneous field. So the same result as we derived using the Einstein elevator. Questions, comments? Isn't this beautiful? All right. So really, we now know everything we need to know about the gravitational redshift, right? And so, for the static observers, this beautiful formula. The moving observer, you will study in tomorrow's lecture.
When you're talking about the Newtonian limit and you put the phi in there,
yeah,
you're thinking in this Newtonian potential that is caused by a mass, right? Not by energy, for example, a photon.
Of photon?
Yeah, like photons in general relativity are, well, they are energetic. So
well, that's right. So everything with mass is gravitating. The gravity is universal. So whatever has any energy, momentum, any mass will gravitate and will curve the space-time. However, here typically, if you have small particle or whatever, the curvature is too small. So here I'm really talking about like massive objects, like I'm studying whatever happens, on the surface of the Earth. So that's the thing which the Earth is causing this potential phi.
Why did you take the ratio of the frequency with the ratio of the proper time and not full time?
Oh, I'm just using the fact that the frequency is given by inverse 1 over time, right? So let's say my clock, has some things in them which basically oscillate or whatever, and so the frequency tells me, if I increase the frequency, the proper time.
Why is it proper time but not the regular time coordinate?
Well, okay, so very good. That's a very good question. So of course, what you are trying to do is that you are trying to set up an observer who is sitting at rest and looking at his own clock. So the clock of the observer, in principle, has nothing to do with the global time or with the time coordinate in the space-time. So time coordinate in the space-time doesn't mean anything. It's simply just a coordinate which you use to label your events in the space-time. But what the observer really measures is the time on his clock, and so that's the proper time. That's a good question. All right. So now, where are we going with this? So what is the big overview of things? So, but EF, probably F, maybe G, field theory for gravity. And so now let's just look at what we know about the classical field theories, and there is 3 of them which are really important. Of course, you have many more, but these are the most important field theories. So let me make a table. I have the Maxwell theory here, and then I have the Newton theory here, and then I have the Einstein theory here. Einstein theory here, Maxwell here, and Newton. So, as always in the field theory, you have to identify what the right field is, right? So we need to say what the field is. Well, we know that the field in the Maxwell theory is, for example, the 4 potential A mu. Okay. We know that the field in the Newton theory is the Newtonian potential phi. And I was trying to convince you today that the right field for the Einstein theory is just the metric. So G mu nu. This is a gauge theory. That is a gauge theory, which is telling you not all the components of A mu actually are physical. We know that if you have just the Maxwell field on its own, we have only two true degrees of freedom, which correspond to two polarizations of the photon. So not all these 4 are independent. You also remember the beautiful formula about counting degrees of freedom in the gauge theories for gravity, and again, only 2 degrees of freedom are hiding in the G mu nu. But let's leave that aside. So now you have the field equations. Okay, so this is simple for Maxwell. So that's just box on A mu is minus 4 pi J mu, and we also have to have the Lorentz gauge condition. So that's the field equations for Maxwell. And then we have also the equations of motion, and that's just the Lorentz force law. dP mu, d tau equals to E F mu nu u nu. Okay, so we know everything about the Maxwell theory. So now what is the analog of the field equations in the Newton theory? Poisson equation, exactly. So nabla square on phi is 4 pi G Newton times rho, where rho is the matter density. And here we have just the Newton law, dP over dt is minus m nabla phi. Okay. Do we know what the equations of motion are in Einstein theory?
This particle,
Uh-huh.
the geodesic.
The geodesic equation, exactly. So we already know half of the theory here. So here we have the p mu over d tau. Let's write it in terms of the momenta, plus gamma mu alpha beta p alpha u beta equals to 0. So our geodesic equation is precisely, the equation of motion in the gravitational field. Okay. So now you see that you know 2 out of 3 ingredients of the Einstein theory. You identify what the field is, and you know what the equations of motion are. So what remains, of course, is to find the field equations for the Einstein's theory. Okay. And that took Einstein some time because he had to learn the differential geometry. So, as I said, it took him a couple of years to learn differential geometry and to understand what the field equations should be. And unfortunately for him, he actually gave a seminar to Hilbert about what he's trying to do. And of course, Hilbert being the greatest mathematician of the time, he came up with the answer a couple months before Einstein. Okay, so once Einstein gave the seminar, Hilbert knew the answer immediately, and it took another time for Einstein to actually come up with his own derivation of the field equation. That's why we sometimes call it Einstein-Hilbert action, which derives the field equations, because actually Hilbert was the first one to find. So anyway, a spoiler, we already know what these equations have to be. A spoiler. So now you will see that this, why it took Einstein so long, nobody knows, right? So you know that in the static limit, the Einstein field equations have to reduce the Newton equations, right? So we have to have in the static limit nabla square on phi equals to 4 pi g rho. But we also know from the Newtonian limit, which Einstein knew then, is that GTT is related to my Newtonian potential phi. Okay, so this is my GTT, and it contains phi in it. Okay, so now if I write nabla square on GTT with a minus sign, I'm getting whatever this is. So you can write down that the Poisson equation, so Poisson equation can also be written as minus nabla square GTT. So GTT has the 1, which doesn't do anything, but it has the 2 phi in it. So this is actually 2 phi. And this is equal to, and there's a minus sign. That's equal to minus 8 pi g rho. Plus probably. Yeah, if I put a minus here, that's a plus. 8 pi g rho. But you also know, and Einstein knew that the energy density is nothing else than the TT component of the energy momentum tensor. Okay, so this is 8 pi g t dt. Okay, so energy momentum tensor contains the information about the energy density, and so we have this equation here. So now you want to make this to be an equation which is valid in all frames. So in other words, you have to make it a covariant equation, you have to make it a tensor equation. Well, the only generalization of TTT is that you somehow write T mu nu. Okay, so we have 8 pi g T mu nu, and then this has to be something, some differential operator acting on my metric. But because the right-hand side has 2 indices, the left-hand side has to have 2 indices. So let's call the left-hand side G mu nu. And where G mu nu is such, so G mu nu is an operator which contains the metric, the first derivative of the metric, and two derivatives of the metric, such that in static limit, it gives g mu nu, well, g dt equals to minus nabla square g dt. Okay, that's the requirement. Okay. Okay, but actually you know even more than that. You know that the energy momentum tensor is conserved in special relativity. Okay, so the energy momentum tensor satisfies the conservation equation d mu t mu nu equals to 0. So now, as we will see in a minute, and Einstein knew that, is that to make this general relativistic, to make it covariant, so that this is also true in the presence of gravitational field, you simply replace the partial derivative with this covariant derivative. So nabla mu t mu nu equals to 0. So that's what Einstein knew already, a long time ago. Yes.
Was the energy momentum tensor used in physics before general relativity?
Say it again.
Is the energy momentum tensor used in physics before general relativity?
Well, certainly for special relativity. Yeah. So the energy momentum tensor,
Like
for example, for the Maxwell theory, people knew very well like the spatial paths of like the stresses of electromagnetic fields and whatever. So what really special relativity did is that it gave an interpretation for T00, which is the energy density, and T0i. So people just knew all the equations. They just combined them into a tensor equation to have special relativity, right? So certainly they knew T mu nu before general relativity, and Einstein soon realized that this must be true in general. Okay, so he knew also this, but of course. So now I apply this nabla mu on both sides of the equation, and so I have nabla mu t mu nu equals to 0. So I better have nabla mu g mu nu equal to 0. So consistency requires nabla mu g mu nu to be equal to 0 as well. Okay, and so now your problem is actually well posed. So now you ask your so this is your problem, right? You are trying to find the differential operator g mu nu, which depends at most on two derivatives of the metric, such that in the static limit, meaning whatever, it reduces to this, and moreover, it satisfies an equation nabla mu g mu nu equals to 0 for any metric. So now you ask your mathematician friend. In case of Einstein, it was Marcel Grossmann, and he immediately tells you, well, there is only one such g mu nu, and it's given by the Einstein friend. Okay, so Grossmann double n. I'll tell you g mu nu is the Einstein tensor. Okay, so this is what really took Einstein, a couple of years to figure out. And you see that you can do it, on this half of the blackboard, plus one line here. Okay, so that's the spoiler. But of course, to understand this, you need to understand a little bit of differential geometry, and so that's what we will be doing now. We'll be studying the differential geometry a little bit, and I'll just convince you that I'll try to convince you that really there is only one such g mu nu which satisfies this nice property. Are there any questions? Yeah.
Why can't g mu nu depend on higher derivatives of the metric?
Oh, well, in principle it could, but as always, you don't want higher than second derivatives in your equations, in your physical equations, because you simply have too many solutions, and some of these solutions are typically bad. You have these runaway solutions, and you have ghosts at the quantum level, and so only the second order equations are typically physical. So that's why you want this, only two derivatives. If you can. Sometimes you cannot avoid it. Sometimes you have to write many derivatives, but if you can avoid it, let's try to avoid it. All right. So more questions? So now this is where we are heading. So we are trying to find the field equations, but for that we have to understand some geometry. So chapter 3 will be geometric tools. And part A will be manifolds. So let me draw one for you. And it can have some holes in it and whatsoever. So imagine this ugly object here, but you will call such an object a manifold as long as if I take any point on this manifold, locally the region will look like the vector space R to the n. Okay, so this locally has to look like R to the n. And moreover, so I can always find a coordinate system where the neighborhood of this point will look like R to the n. However, it may happen that I have another coordinate system which also looks like R to the n, and the point actually belongs to both of them. So then you will call this manifold, this object a manifold, if a transformation from one coordinate system to the other one is nice and smooth, meaning C infinity, so infinitely differential. Okay, so let's just make this. Okay, so n-dimensional manifold, n-dimensional. This is a vague thing. Dimensional manifold. I'll give you a definition in a minute. Has a local differential structure. Of R to the n, but not necessarily its global properties. So what I mean by that is that typically you won't be able to describe the whole manifold by just one coordinate system. So simply, the coordinate system will break down somewhere, and then you need another coordinate system, and that means that you don't have the global properties of R to the n. So in the local, it looks like R to the n. Okay, so let's have a formal definition, which will be horrible. And this is not a mathematical definition; it's a physical definition. So it will. So if you are mathematically minded, you will probably lose all your hair. So anyway, so n-dimensional manifold M called M, and now it starts is a set of points So this is first imprecise statement. Together with a collection of subsets. Let's call them O alpha, such that, and then there will be three requirements which I require. So we have the points, and then we have some subsets there. So first, each point, each P which belongs to the manifold lies at least in one O alpha. So what it means is that O alpha cover M. So it cannot happen that it would have a point which wouldn't have the corresponding subset where it belongs to. Okay, that's the first requirement. The second requirement is that for each alpha, there is one-to-one onto whatever that means map psi alpha, which maps this set of points or the subsets O alpha to new subsets U alpha, which are open subsets of R to the n. Subsets of R to the n. So R to the n is a nice space, and so we want, there's always a map which maps whatever is happening on the manifold to some subsets in R to the n. Okay, and finally, third, and there's no space, let me write it here. So number 3 is that if any two subsets, any two sets, O alpha and O beta overlap, that means O alpha, O beta is not equal to 0, then the corresponding map psi beta composed as psi alpha minus 1 is infinitely differentiable, C infinity. Okay, so this is what a manifold is. So this looks complicated, but actually it is not. So as I say, what it means is that the manifold locally looks R to the n, and that you may not be able to cover the whole manifold with, one set of coordinates, but if there is an overlap of coordinates, this overlap is really, really nice, and then these coordinates and the change of coordinates is actually differentiable. So in other words, manifold is made of pieces. That's no longer a definition, it's just a remark. Made of pieces that look like open subsets of R to the n that are tuned together smoothly. All right, so we have the definition. You have two vague statements that it looks like R to the n. So let's have a picture. So the picture, very simple. So this is my manifold. Let's draw only one hole here. And so now let's take any point on the manifold. This is my point P. So then the statement is, this point has to have some open subset O alpha, which actually contains this point P. Okay, so this point has to be contained in some O alpha. So that's the first statement. Each point P lies in at least one O alpha. Then the second statement is, for each alpha, there is this one-to-one onto map, which maps this O alpha to some open subset in R to the n. So I have R to the n somewhere here, R to the n here. And then the statement is, there is an open subset. So this is basically like the image of this point P. well, not really. Okay. As the image of the point P. And this is my U alpha. And it's simply there is a map which maps this O alpha region to the U alpha region. And the map is called psi alpha. Okay, so in other words, whatever this set describes looks like an open subset of R to the n. Okay, so that's the point number 2. Finally, the point number 3 is, well, let's assume that P actually belongs to more than one O alpha. So there is another O beta, and P belongs to this O beta. Of course, what it means is that there exists a corresponding map, psi beta, to another R to the n. And then this is my point P again. Well, the image of the point P. But there's this map, psi beta, which maps this to U beta. Okay. And then what you require is that you can make a map. You can use these maps psi alpha and psi beta to actually make a map like this from one R to the n to another R to the n. So what is this map? So this map is I can get this map by going first here and then going there. Okay, so this map is psi beta minus 1 composed with psi alpha. Okay, so this map is just maps something in R to the n to something to the R to the n. So normal differential calculus, right? So I have just R to the n to R to the n calculus. Okay, and so what you require is that these psi alphas and psi betas are such that the map going from R to the n to the R to the n is actually nice. It's C infinity. Sorry?
Psi alpha and psi beta inverse should be the other.
Yes, thank you. Of course. Other mistakes?
It only acts on the intersection.
Yeah, exactly. So this is true only in this region where there is an overlap, where you have an overlap of the map psi alpha and psi beta. So let's say, this is, let's say, this part here, and there is that part there, and you can only map in that intersection. Okay. So this is what it is. So now imagine, why this definition is extremely useful is that although this manifold itself is an alienic object, right? So it doesn't have to be embedded in any space. It's very, very abstract thing. But you don't need to know anything about the manifold. All you need to know is how to do calculus in n-dimensional space R to the n, right? And so you will be mapping everything. You'll be using always these maps to map everything to whatever you know from calculus in many variables.
Don't you need to ask this manifold or this set of points to be to have a Hausdorff topology?
Well. This is yeah. There's many. I don't know if you exactly need that, but there's many things which I'm throwing under the carpet here. So the first thing is you should object to is it is a set of points, right? So that's something which is really, really vague. Yeah. but this is good enough for physics. So and really what really matters about the manifolds is I have these nice maps to R to the n, and then I can do just the normal calculus in R to the n.
It is important for physics because we want a region small enough that you can consider it Minkowski.
Okay.
You cannot separate 2 points with different neighborhoods. You would need to have Minkowski idea.
I agree. Yeah. Okay. Is it really important? Yeah. Yes.
Why are we demanding the open subset? Why not a closed? What would have been the problem?
It's always open subsets. I think the problems would be the boundary is typically problematic, so that's why people So don't do it, because then you have to actually talk about, how, people don't consider the boundaries.
I think if you made them closed, it would give the manifold a boundary.
It would give the manifold.
If you wanted the manifold to have a boundary, you'd have to consider closed subsets to be closed.
Right.
What do you mean by a manifold to be closed?
No. So she's talking about the manifold with the boundary.
But,
So you can place a boundary for the manifold. But typically boundaries are problematic to deal with. So let's stick to this.
we can consider
Is it perhaps that we're dealing with open subsets because the continuity in the topological way is defined as mapping open subsets to open subsets? So in order for our maps to be continuous, they need to be able to map open stuff to open stuff. So that
Sounds good to me. Yeah.
Which, it's a mathematical thing, but yeah, that topology then again is just something to declare an open subset.
Okay, so let's have some examples. So one example is the sphere. So the d-dimensional sphere, just a ball here. Everything is nice and smooth on the sphere. Of course, you cannot cover sphere with just one coordinate system. So you can do it up to a point, right? So you have these various mappings. Well, you map it to a complex plane up to some point or whatever. So typically people consider, I have one set over here, and then I have another set over here, and then so you have two sets to compose a sphere. Another example would be a torus. So it's simply, you can imagine torus as a square where you identify this guy with that guy and this guy with that guy. And of course, how it looks like then, it gives you the donut. Okay, so that's another example of a manifold. And then I have this stupid example here of the light cone. Is this a manifold? Exactly. So it would be apart from this very point here, which actually, screws things up, and it's not nice and smooth, and it doesn't have the right dimension. So this is not a manifold. Okay. Very good. So now a little bit more terminology. So these things, these maps psi alpha, they are sometimes called charts in mathematics, or they are called coordinate systems. Coordinates in physics. So they are basically the same thing. And then you see that you have this set of these regions O alpha plus the region of the charts. And so if you have lots of charts, you know that you have an atlas, right? So that's another terminology. So you have the pairing O alpha, psi alpha is called atlas. We will never use that terminology anymore. But we will use the coordinates terminology, not the chart terminology. All right. So you see that a manifold is really, really a simple object. So just a warning, you shouldn't be really thinking that the manifold is embedded in some higher dimensional space. It can be, but it doesn't have to be. Right? So manifold is simply an abstract object which lives in its own space, and you can talk about it by using these maps. Right? So now, however, there are some embedding theorems which tell you, well, actually, whatever the manifold I have, I can embed it into some higher dimensional space. And if you've seen the movie Beautiful Mind, I think, about Nash, yeah, so he was one of the people who created these embedding theorems. It's like really fancy mathematics that you can always embed it. But the space has to be of sufficient dimensionality. So, for example, if you want to embed a four-dimensional Minkowski, four-dimensional manifold, four-dimensional space-time, it's not enough to use, for example, five-dimensional space or whatever. You have to go to sufficient dimensionality. Okay, but it's better not to think for physics again or for anything. It's better not to think about manifolds to be embedded anywhere. It's better to keep think about them like their entities on their own. All right. So we have the stage, we have the space-time. Of course, the manifold will be the space-time. So we better place some objects on the space-time, on the manifold. And the simplest object you can place on the manifold is the scalar function. All right, so a scalar function f is simply a map which maps from the manifold to real number. So this is my manifold. I have some point P here, and then function simply maps this point into my real line here. So this will be f of P, function f, and it gives me some number f of P. Okay, so again, how do I define this? Well, typically people consider, so it's obvious that, whatever the value I'm getting simply depends only on the point P. So if I have one point P, I get some value. If I have another point Q, I get another value and whatever. So now how this is really understood is that you say, I use these charts which I have in my disposal. So then you have one chart O, which maps to R to the N, and so that's my point here. So that's my coordinate system X, or the map X. And I can have another one here, which is O prime, and that maps to R to the N. And then I'll have X prime here. So X and X prime is really the map. So this is X of P, this point here, and X prime of P is that point there. And then it's obvious that what you have to have is that if you map from R to the N to R, you have to have the same number as if you map from this R to the N to R. Okay? Because it's only the value which depends on the point P, right? So what you just derived is that f of P, which is what I want to define, but I want to define it in terms of the coordinate systems, is the same as if I do fx of P or fx prime of P, right? So it doesn't matter which coordinate system I use. It doesn't matter whether I use this map here or that map here, because I just want that value f of P, which is just one value here, right? And so you are deriving the transformation property for the scalar, and people don't write this P, and then they just write f of x equals to f of x prime. Or f prime x prime. Okay, so this is how the scalar transforms. But you see that all you are capturing is the fact that you just want to map, you just want to assign, to a point some concrete number here. It doesn't matter if you do it in this coordinate system or in that coordinate system.
Question.
Yes?
What does the prime on f means? Like prime on x means you're using another coordinate system.
So this x prime means I'm using the new coordinate system, and in principle, this could mean a different. If I do like a coordinate transformation, the object in principle could change, and so that's why I put prime here. But what it really means is that this is f of P, right?
Yeah.
All right. So now this is just a map from manifold to real number. So that's a scalar function. of course, you can consider more complicated functions, and you can consider functions which go from manifold to a manifold. Okay, so then again, this is defined through these maps. So if you want to, map a function f going from one manifold M to another manifold N, well, again, I want to map some point P to some other point here. Well, then you have the corresponding map here to R to the N. And here you have also the corresponding map to the R to the N. And how you define this function, so this is my map psi, this is my map psi prime, and how you define this point going to that point, so you say, I have this point going to that point, so I can use that. So this map between R to the N and that R to the N is simply psi prime composed of F composed of psi prime. And then you are again doing the calculus between R to the N to R to the N. Okay, so this is how you define the map between the manifolds is through this map here.
The dimensionality of the manifolds has to be the same?
They don't have to be the same. You can have maps between various manifolds. You can show that if they have the same dimensionality, and if the map is nice, meaning it's C infinity and it's invertible and whatever, then actually these two manifolds can be considered basically the same manifold, and then you call the corresponding map a diffeomorphism. So it's a very special, nice map. So if F, which maps M to N, is C infinity, it's 1 to 1, and it's onto, and has C infinity inverse. It is C infinity and has C infinity inverse. Then the map is called diffeomorphism. It's called diffeomorphism. And you can show that diffeomorphic manifolds are basically the same manifold. Okay? You can think about them. M is basically the same as N. Okay? So if there exists such a map, which is a diffeomorphism between two manifolds, then these two manifolds, you don't have to distinguish them. They are basically the same manifold structure. All right. So now we have been talking about particles a lot, and we have been talking about strings and stuff like and objects like this. So what does it really mean that I have a curve in my space-time? So what does it mean I have a word line in my space-time? What does it mean I have a word sheet in the space-time? Well, you have to define what a curve on a manifold is. And it's done very simply. So you say a curve, let's call it gamma, on the manifold M is a map which maps an interval which is a subset of R1, a region in R1 to manifold M, such that if you use your map again, so psi alpha composed with the map gamma and then t, so whatever it is, it's just x1 of t, x1 of t, x2 of t, and so on, is nice and smooth. Okay, so what the picture is, I have my manifold, And then I have an interval I, which is a subset of R1. And then on that manifold, there is basically your where your parameter t lives. And then the gamma is simply a curve, is simply a map, which maps this interval I to a manifold. So this is a gamma, and then you get a piece of a curve on that manifold here. So gamma is a map which maps the interval to the manifold. And then I say, well, something composes, something has to be smooth. So again, I am using the differential structure of the manifold. So I know that there is a map psi going to R to the n. So that means that in R to the n, I will have a curve as well. And that's described by x mu of t. And then you require that the map going from the interval to my R to the n, which of course is simply given by psi composed with gamma, is smooth. So the map from R1 to R to the n is smooth. Does it make sense? It's like, you know, always using these maps R to the n, always mapping everything into whatever you know from your calculus. And of course, we know that this is a very important example for particles in general relativity, because this precisely describes the word line of a particle, right? It could also describe a river on the Earth or whatever. Okay. So similarly, a surface is just a two-dimensional generalization of this. A surface S is a map which maps U, which is a subregion of R2 now, to my map, to my manifold M, such that psi alpha composed with S. Now you have two parameters. Let's call them tau and sigma, which is x1 tau and sigma, x2 and of tau and sigma, xn tau and sigma is smooth. And it's a direct analogy with this. So now I have R2. I have a subregion of R2, which is my U. I have this thing here. I take my coordinates in R2 to be tau and sigma. Tau and sigma. And then you map this to your manifold. So this is your S. Is my manifold here. And I map this to some subregion in my manifold S. And again, I have the chart psi to R to the n. And I have the corresponding region here. And then you require that the map going from R2 to R to the n is nice. An example of this would be the worldsheet of the string. But it would also be a lake on the Earth. Or New York City, okay? Are there any questions to this? It's easy peasy, right? It's really logical and nice, yes?
Because we were mapping this word lines to the Minkowski space, right?
Very good. So here I'm saying R to the n, because I am discussing Riemannian geometry. Riemannian geometry is really I'm having Euclidean space in all n directions. What we will need for space-time is that actually this thing is the Minkowski space, right? So we will have a different signature. So actually for relativity, you need pseudo-Riemannian manifolds, pseudo-Riemannian geometry. Yeah, that's a very good point. Other points like this? All right, so I want to make this lecture really short because it's really late and everybody is tired. So the next thing which we will have to do is that we have the manifold and we understand how the curves on the manifold live and how the surfaces can be described on the manifold and how the scale functions live on the manifold. But of course, you know that physics is mostly described by vectors and tensors and stuff like that. So the next step will be to introduce these more complicated objects like vectors, tensors, and stuff like that. And let's do it tomorrow. Okay? So then we have to place these tensors on the manifold, and once we have the tensors on the manifold, we can do the differential calculus of these tensors, and we can write down the field equations for physics. So let's do it tomorrow. Thank you.